So previously, by making a very bold assumption that the sine function can be factorized in the same way that polynomials can be, we were able to evaluate zeta of 2k for all positive integers k. And in particular, we found that the sum of the reciprocals of the squares of the natural numbers, which is zeta of 2, equals pi squared over 6. And of course, we would like to rigorously prove this factorization of the sine function. However, before we even try to do this, we might want to try to obtain this sum in a way which does not involve making any assumptions. So we would like to completely rigorously prove this. And this is what we will do in this video. And we are going to start by a lemma which relates the sum of the reciprocals of the squares of the odd positive integers to zeta of 2. And we are going to show that this sum equals 3/4 of zeta of 2, and it is quite easy to do this because we can write zeta of 2 as two infinite series, one of which involves only the even terms, while the other one involves only the odd terms. And then 1 minus 1 over 2 squared times zeta of 2 equals zeta of 2 minus 1 over 4 times zeta of 2. And we write this first term as the infinite series involving only the even terms and the infinite series involving the odd terms, but we leave the second term as it is. When we do this, we will find that the first and the third summands cancel, leaving us with only the sum of the reciprocals of the squares of the odd positive integers. And this proves the lemma. Now we'll jump directly to proving that zeta of 2 equals pi squared over 6. And to do this, we start with the sum of the reciprocals of the squares of the odd positive integers. And we rewrite them as 1 plus 1 over 3 times 3 plus 1 over 5 times 5, and so on. And the reason we write it in this way is because we can multiply each term of this infinite series by a fraction equal to where the numerator equals the product of the odd numbers, while the denominator equals the product of the even numbers. So the first such fraction is 1 over 2, the second one is 1 times 3 over 2 times 4, and the third one is 1 times 3 times 5 over 2 times 4 times 6, and so on. But then in each term, so that the overall effect is the same as multiplying by 1, we are going to multiply by the reciprocals of these factors. And the reason we have done this is because these terms in the brackets, that is 2 over 3, 2 times 4 over 3 times 5, 2 times 4 times 6 over 3 times 5 times 7, and so on, they are actually expressible as integrals as follows. So we are going to prove this fact at the end of the video, which is another lemma. But for now, let us continue forward with our proof. And we can write this whole expression instead of an infinite series of integrals, we can write it as an integral of an infinite series as follows. And when we look at the infinite series here, we find that we can rewrite x and x cubed over 3 and x to the power of 5 over 5 and so on as integrals themselves as follows. So and once again, we are going to write this sum of integrals as the integral of a sum as follows. And now when we look at the infinite series inside this second integral, we know from the binomial theorem that this is equal to 1 over the square root of 1 minus t squared. And so the sum of the reciprocals of the squares of the odd positive integers is equal to this double integral here. So very well. Now, let s be between 0 and pi over 2, and let us put x equals the sine of s. Because s is restricted to this domain, s equals the arcsine of x because s is well defined. And dx equals 1 minus x squared times ds, so we take the positive square root as s is between 0 and pi over 2. And so s itself can be expressed as this integral, that is the integral from 0 to x of 1 over the square root of 1 minus t squared. Okay, so now we can write s ds as this differential here, so 1 over the square root of 1 minus x squared times the integral from 0 to x of dt over 1 over the square root of 1 minus t squared times dx. And we can integrate from x equals 0 to x equals 1 to find the double integral we found previously. And also the evaluation on the left is very easy because when x equals 0, s is equal to 0. But when x equals 1, then s is equal to pi by 2, which is the whole arc in the first quadrant. And so pi squared over 8 is equal to this double integral which we found previously. Which means that the sum of the reciprocals of the odd positive integers squared equals pi squared over 8, and as we showed in our first lemma, this is equal to 3/4 of zeta of 2. And from this we conclude that zeta of 2 is itself equal to pi squared over 6. So the only thing that remains to be done now is to prove this lemma that we made use of in our proof, that the integral from 0 to 1 of x to the power of 2n plus 1 over the square root of 1 minus x squared equals the fraction where the numerator is the product of the first n consecutive even numbers, while the denominator is the product of the first n plus 1 odd numbers. And we are going to achieve this by induction. So to achieve, before trying to prove this by induction, we need to find a reduction formula for this integral. And so we are going to integrate by parts. So we put u equals x to the power of m minus 1, and dv by dx equals x over the square root of 1 minus x squared, so that u dv dx equals x to the power of m over the square root of 1 minus x squared. And then we find du by dx and v. And when we put all this in the formula for integration by parts, we are able to relate our integral in the case where the exponent is m to the case where the exponent is m minus 2 by rewriting this square root here as 1 minus x squared over the square root. Which means that if m is positive, this term vanishes in the limits x equals 0 and x equals 1, leaving us with this reduction formula. And now we are ready to start the induction. We let Pn, where n is a positive integer, be the statement that we would like to prove. And we are going to prove P1 very easily by making use of our reduction formula. And then we can integrate this by inspection to find that it is minus the square root of 1 minus x squared. And it vanishes when x equals 1, but when x equals 0, it equals minus 1. So this integral equals 2/3, which means that P1 is true. So this establishes the base case. And now we are going to assume that Pm is true for some positive integer m. And when we apply our reduction formula, since we have assumed that Pm is true, this integral here is equal to the product 2 times 4 all the way through 2m and over 3 times 5 all the way through 2m plus 1, which means that pm plus 1 holds. So pm implies pm plus 1, and as p1 is true, therefore pn holds for all integers n greater than or equal to 1. So in this way, we have been able to completely rigorously prove that zeta of 2 equals pi squared over 6. So we have not made the assumption that sine of x can be factorized in a way analogous to factorizing polynomials. But in the next video, we are going to prove that sine of x has this factorization.